This is machine learning models for identifying risk factors and prediction of ALS progression. This is a joint work performed by Lawrence Livermore National Laboratory and the United States Veterans Affairs Palo Alto Healthcare System. Our work focuses on using large-scale electronic health records datasets to find factors which are commonly available in clinical records that can also function as surrogates for ALS functional rating scale scores. Functional rating scale scores are the clinical gold standard for defining progression of ALS over time. Here, they are referred to as FRS scores. FRS scores are measured by recording a patient's ability to perform a variety of tasks, such as eating, bathing, and dressing themselves. Unfortunately, FRS scores are difficult and time-consuming to measure, and as a result, they are not collected often. The method we propose combines an autoencoder network to perform dimensionality reduction on the input data and a recurrent neural network to do temporal learning over the compressed data. Combining these neural networks allows us to predict FRS scores 20 to 40 days into the future while only using 3 months of past patient vital signs as input. Our network architecture is outlined on the poster, and the input data comes in with 27 features per measurement. Then it is passed through the autoencoder and is compressed down to 8 features per measurement. The RNN then takes the compressed sequence as input and returns a prediction of the patient's future FRS score. The training procedure first trains the autoencoder to perform dimensionality reduction on the data. Then, the data is compressed using the trained autoencoder. Finally, the recurrent neural network is trained to predict future FRS scores by minimizing the root mean squared error, and the recurrent neural network is given only the compressed data as input. Our results show that machine learning models can learn to pay more attention to clinically relevant features, and that our combined autoencoder and recurrent neural network perform best. In the first table, we see that even simple machine learning models can learn to identify clinically relevant features. The random forest learns to attribute greatest importance to weight and height, which combined can be used to infer BMI, an important indicator of ALS progression. The second figure illustrates that the recurrent neural network is also able to detect important features, as we see the largest important attribution around features like pulse and respiratory rate. Finally, our third figure shows that the combined autoencoder and recurrent neural network achieves the lowest root mean squared error on the FRS prediction task. Additionally, we find that a model trained on only a subset of identified important features can still achieve a root mean squared error within 15% of the model trained on the full feature set. Thank you for watching.